So here are the requirements. We'll first require is an empty jar, and we'll require some water. Then we'll need some A4 sheet cutouts. I've already made those cutouts, so we require tapes and scissors for that. We'll require some soap. And of course need a laser. So the procedure, let's get started. So here I've already made a cutout and I've pasted tapes on both the edges. I'll paste it white sheet on the back of the jar so that things can be clearly visible. Now let's put the soap and mix the soap with the water to make it a little colloidal so that the path of the laser is easily visible, as a colloidal solution can partially reflect the path of the light. Now we'll pour this water into this jar. Let's keep other things aside. And now we are pouring water into this jar. Let's close the jar with its lid. Now we'll use some books to level up this jar so that the experiment can be performed easily. Now let's keep this jar over these books. Lights off please. Now here I have turned on my laser. Now we can see the path of the laser very clearly. Now I'll try increasing the angle of incidence. As you can clearly see, all of the light of the laser is getting reflected back into the medium of water, and there is 0% refraction, that is 0% of light is going out. This phenomenon is known as total internal reflection. I am shining this laser light from the right hand side of the container, and you can see light after getting reflected from the water coming out after refraction from the left hand side of the container by seeing the dot on the white paper at the left hand side of the container. We can talk about the mathematics of this in the conclusion part. Now let's see another example. Now in this case, I have made a hole in this bottle filled with colloidal water. I've placed my hand over it to stop air coming in. Now I'll release my hand and allow water to come out. Lights off please. Now as we shine this laser, we can see the water coming out is illuminated, which directly means that light is getting bent along that water coming out. Now we'll jump into the theory and the conclusions of the experiment. This is a diagram to show you. This is the incident angle, this is the incident ray, this is the refracted angle, and this is the refracted ray. The refracted angle will always be greater because light is coming from a denser medium to a rarer medium, and the refracted ray bends away from the normal, so the refracted angle is always greater than the incident angle. So now when we start increasing this incident angle such that when the refracted ray moves down, it moves down like this and reaches the 9, it becomes normal to the normal. And this angle, when the refracted ray grazes through the surface, this angle is known as the critical angle. And any incident ray and any incident angle greater than the critical angle makes the refracted ray reflect back into the same medium from which it was coming. And this phenomenon is known as total internal reflection. Now let's talk about observing TIR in nature. The glaze of a diamond. We all know how a diamond shines. It's all because of total internal reflections that is happening in between the diamond. And the mirages, of course, are all caused by total internal reflections, where there are differences in optical density because of the temperatures in the difference in temperatures in the air. This is a very common example of optical fiber. It helps in communicating over large distances and is always based on TIR. And this binoculars is also based on total internal reflections, which are occurring over here. This is the mathematics of TIR. This is the Snell's law, and we can find out after calculating that the incident angle should be greater than sine inverse of 1 by mu of water. And this is a clip from the experiment so that you can relate the theory from the practical. In the last, I would like to thank Optical Society IIT ROPAR for this opportunity. Thank you.